Have you ever pondered about the origin of everything that surrounds us? Where did the universe come from? These questions have always intrigued mankind, leading us to embark on a journey through the cosmos, trying to understand our place in this unfathomable expanse. The universe, in all its grandeur and vastness, is an enigma. Its origin, a mystery that we've been trying to unravel for centuries. Over time, we've formulated countless theories and hypotheses, each one attempting to explain the birth of the cosmos in a different light. From ancient cosmological views, filled with mythical beings and celestial gods, to modern scientific theories grounded in astrophysics and quantum mechanics, our understanding of the universe's origin has evolved tremendously. Yet, amidst the myriad of theories, one stands out. One that has been subjected to extensive scrutiny, yet continues to hold its ground. One such theory that holds considerable weight among the scientific community is the Big Bang Theory. The Big Bang Theory, in simple terms, proposes that the universe began from an incredibly hot and dense point roughly 13.8 billion years ago. This point, known as a singularity, is a concept that might twist our minds a bit. Imagine all the matter, energy, space and time in the universe compressed into an infinitesimally small, infinitely dense point. Yes, that's a singularity. Now you might be thinking, how can something so infinitely small contain so much? Well, that's the beauty and mystery of our universe. The Big Bang Theory suggests that our universe began from such a singularity. The initial conditions were incredibly hot and dense, quite unlike anything we can conceive in our current universe. From this singularity, the universe began to expand. Not into something, but as something. It's a common misconception that the Big Bang was an explosion that happened in space. Instead, it was an explosion of space. The Big Bang produced not an outward blast of material, but an outward stretching of space itself. As the universe expanded, it also cooled down. The immense energy present during the initial moments of the universe began to transform into various forms of matter and energy that we see today. This process was not immediate, but took billions of years. The Big Bang Theory also suggests that this expansion is still ongoing. The universe continues to stretch and grow, with galaxies moving further and further apart. So, when we talk about the Big Bang Theory, we're discussing the birth, evolution, and future of the universe. We're delving into the roots of everything we see around us and beyond us. We're trying to understand where we came from and where we're going. So the Big Bang wasn't an explosion in space, but rather an explosion of space. So, what happened after this massive expansion of space? How did we get from an extremely hot and dense point to the universe we know today? In the immediate aftermath of the Big Bang, the universe was a seething cauldron of energy and matter, too hot and dense for atoms to form. However, as space continued to expand, the universe began to cool down. This cooling process took place over hundreds of thousands of years. As the universe cooled, particles of matter started to come together, forming protons and neutrons. These protons and neutrons then began to combine, forming the nuclei of the simplest elements, hydrogen and helium. This period, known as the era of nucleosynthesis, marked the birth of the first atoms in the universe. But these were not yet the atoms as we know them today. They were ionized, meaning they were so hot that their electrons were stripped away. As the universe continued to cool and expand over hundreds of thousands of years, these atoms gained their electrons, becoming neutral. This was a pivotal moment in the history of the universe. The neutral atoms could now clump together under the force of gravity, setting the stage for the formation of stars and galaxies. And so, over billions of years, these atoms clumped together to form stars. The stars, in turn, clumped together to form galaxies. Meanwhile, heavier elements were formed in the hearts of stars through the process of nuclear fusion. These elements were then spread throughout the universe by supernovae, the explosive deaths of stars. These processes of star and galaxy formation, nuclear fusion, and supernova have continued over the eons, leading to the universe as we see it today. A place of incredible diversity and complexity, with countless galaxies, stars, planets, and the building blocks for life. In essence, Every atom in our bodies, the Earth, the Sun, and even distant galaxies, can trace their origins back to this event. But how can scientists be so sure about an event that occurred billions of years ago? Well, it's all about the evidence. The Big Bang Theory isn't just a wild guess or an imaginative story, it's a scientific theory supported by a wealth of evidence. One piece of evidence is the redshift of distant galaxies. As light travels to us from distant galaxies, the universe expands, which stretches out the light waves. This changes their color to the red end of the spectrum, hence the term redshift. It's like the cosmic version of the Doppler effect. The farther away a galaxy is, the faster it's moving away from us, and the more its light is redshifted. This is consistent with the idea that the universe is expanding from a single point, as the Big Bang Theory suggests. Next, we have the abundance of light elements. According to the Big Bang Theory, the early universe was an extremely hot and dense environment where nuclear fusion could occur, creating light elements like hydrogen and helium. As the universe expanded and cooled, this nuclear fusion stopped, leaving an abundance of these light elements. When we look out into the universe today, we see exactly this: a universe filled with roughly 3/4 hydrogen and 1/4 helium. And perhaps the most compelling evidence of all is the cosmic microwave background radiation. This is the afterglow of the Big Bang, a faint radiation that fills the entire universe. It was first detected inadvertently by Arno Penzias and Robert Wilson in 1965. Their discovery earned them the Nobel Prize in Physics. The existence of this radiation had been predicted by the Big Bang Theory years before its discovery. Its detection was a major triumph for the theory. So, the redshift of distant galaxies, the abundance of light elements, and the cosmic microwave background radiation. These are just 3 of the many pieces of evidence that support the Big Bang Theory. These pieces of evidence provide strong support for the Big Bang Theory, reinforcing its acceptance in the scientific community. The Big Bang Theory, while complex, provides a fascinating explanation for the origin and evolution of our universe. We've traveled together from the singularity, a point of infinite density and temperature, to the rapid expansion known as inflation, and the formation of the first atomic nuclei in a process called nucleosynthesis. We've witnessed the birth of the first atoms, and the release of light as the universe cooled, culminating in the cosmic microwave background radiation we detect today. Our journey continued through the formation of galaxies and stars, right up to the current state of our ever-expanding universe. Each of these stages is supported by a wealth of scientific evidence, from astronomical observations to particle physics experiments. While the Big Bang Theory may not answer all our questions about the universe's origin, it certainly provides a compelling and scientifically backed story of our cosmic beginnings.